ASML's extreme ultraviolet lithography machine is the most tightly export-controlled piece of equipment on Earth. It costs roughly $200 million, spans the length of a shipping container, and no country sells one to China without a government license. That machine, the crown jewel of Western semiconductor leverage, runs on magnets Beijing can stop shipping tomorrow. Before you say, they'd just buy magnets from Japan or Germany, stay with me, because that sentence is where the story gets interesting, and it doesn't resolve the way you'd expect. Here is what this actually is: a loop. Every wire you follow from inside a chip-making tool traces back to the same source node. The West spent years building a ceiling over China's chip ambitions, export controls on finished chips, then on the tools that make chips, then on the components inside the tools. This story is about the floor, and the floor was already there before anyone drew the map. By the end, you'll understand exactly what kind of magnet lives inside a chip-making tool and why it matters, why China's position in the magnet supply chain is structurally different from an ordinary supplier relationship, and what the realistic path out of this looks like, and why it's longer than it sounds. There's a word, neodymium, that almost never appears in semiconductor policy discussions. Its absence is the tell. And there's a question sitting underneath all of this. China didn't build this position as a response to chip sanctions. So when did the loop actually close, and did anyone notice? Those two threads run through everything that follows. To understand why just buy from Japan doesn't close the loop, you need to understand what this magnet actually does inside the machine. A photolithography tool positions a silicon wafer to within a few nanometers during exposure. We're talking about the width of a handful of atoms hit repeatedly at speed across an entire wafer. The motors doing that work are voice coil actuators and linear motors. Think of a voice coil motor the way you'd think of a loudspeaker driver, a coil of wire moving through a magnetic field, except instead of pushing air to make sound, it's pushing a wafer stage to a precise location in space, and the tolerance for error is essentially zero. To do that job, the motor needs a magnetic field that is exceptionally strong, exceptionally stable, and fits inside a physically compact stage. Electromagnets can produce strong fields, but they heat up under continuous load. They require constant power, and, critically, their field varies with the current driving them, which introduces noise into a system that needs to be nanometer quiet. The solution is a permanent magnet providing the stable bias field, with the coil modulating around it. You need both, and the permanent side has to be powerful enough to make the whole arrangement work in the space available. Neodymium iron-boron magnets, the dominant type in precision motion applications, produce roughly 5 to 10 times the magnetic energy per unit volume of a standard ferrite magnet of the same size. That ratio is established materials science, and it's why this specific material became the default for applications where field strength, physical size, and thermal stability all have to be optimized at once. There is no industrial scale substitute that matches all three at this performance level. Imagine trying to place a coin on a table to within the width of a single human hair, every time, at speed, thousands of times per wafer. You don't do that with a rubber band and a spring. You do it with the most powerful magnet you can fit in the available space, driven by electronics precise enough to feel the difference between close and there. So the magnet is not optional, and it is not generic. Now follow the wire back one step. Where does that magnet come from? China produces approximately 60% of global rare earth ore. That figure, drawn from sources including the United States Geological Survey and the International Energy Agency, already signals concentration. But ore isn't what a magnet factory buys. What a magnet factory buys is a purified rare earth oxide, a separated, processed input that requires a refining step between the mine and the furnace. And at that refining layer, the concentration is even sharper. An estimated 85 to 90% of global rare earth refining capacity sits in China. That range comes from industry analyst estimates and international energy research. It is a consensus approximation, not a precise audited figure, but no serious analyst disputes the order of magnitude. Think of the rare earth supply chain as a river with 3 dams: the mine, the refinery, and the magnet factory. China controls all 3 dams. You can sometimes route around the first dam by mining elsewhere. There are rare earth deposits in Australia, the United States, and parts of Africa. But the refinery dam is where the river narrows most. The chemistry of separating individual rare earth elements from each other is complex, capital-intensive, and environmentally demanding. China built that capacity over decades, priced competitors out of the market, and now holds the narrow point in the channel. In 2023, China placed certain rare earth products under export licensing requirements, a standing policy mechanism that means Beijing can now require approval for exports that previously flowed freely. This is not a hypothetical. It is documented Chinese Ministry of Commerce policy. The licensing has not been deployed as a blanket cutoff specifically against chip tool magnet supply, but the architecture changed. Before 2023, these exports were a transaction. After 2023, they are a permission. That is a different kind of relationship, regardless of whether the lever has been pulled. Which brings us to the word that almost never appears in semiconductor policy discussions: neodymium. The 2010 to 2011 rare earth price spike, when China restricted rare earth exports and prices for some materials rose by multiples in months, triggered genuine alarm in the defense sector and in consumer electronics. Investigations were launched. Policy attention sharpened, but that attention focused on the materials themselves as commodities and on their role in electric motors, wind turbines, and weapons guidance systems. The semiconductor tooling application, specifically the actuator layer inside a lithography or etch tool, was a smaller, more specialized market, not on the main policy radar. The chip tool supply chain was being tracked at the level of optics, electronics, and software, not at the level of the motors that move the wafers. So the dependency was there. It just wasn't on the map anyone was drawing. Now directly answer the objection. Japan does produce neodymium iron-boron magnets. Shin-Etsu Chemical and TDK are significant producers. The United States has MP Materials in California, primarily mining and early-stage processing, with magnet manufacturing in development. Europe has ambitions. So why hasn't the precision tool industry already diversified its magnet sourcing? 3 compounding reasons, each one making the next harder to solve. First, even Japanese and some other non-Chinese magnet producers source rare earth oxides, the refined input, partly from Chinese refiners. Some industry reporting and analyst commentary indicates this dependency runs deeper than the factory level. If that's accurate, substituting at the magnet factory layer doesn't fully escape the refining node. You've moved one dam, but not the one that matters most. This is reported and analyst assessed, not independently confirmed for specific producers, but the structural logic is consistent with the concentration figures. Second, qualifying a new magnet supplier for a precision semiconductor tool is not a procurement decision. It's a re-engineering and re-qualification process. The magnet's exact dimensions, field profile, and thermal behavior are integrated into the stage design. Changing the source means verifying that the new magnet performs identically in the full system, under all operating conditions, across the full lifetime of the tool. That process can take years, not quarters. Switching magnet suppliers in a precision tool isn't like switching coffee brands. It's closer to redesigning the engine around a different fuel. You can do it, but not in a quarter, and not without testing every assumption the old design made. Third, the scale works against urgency. Chip-making tools are produced in the thousands per year globally, not the millions. The market for high-performance magnets in this application is real, but not large enough to have justified building an entirely separate, vertically integrated supply chain. Until the strategic calculus changed, the commercial case for that investment wasn't there. The loop is real. It doesn't close overnight from either direction. Now ask how it got built in the first place. China began systematically developing its rare earth industry in the 1980s. Deng Xiaoping is widely attributed with the observation that the Middle East has oil and China has rare earths, a framing that, whatever its exact provenance, reflected a genuine long-term strategic orientation. The country used low-cost, state-supported refining capacity to undercut Western competitors. Mountain Pass in California, once the largest rare earth operation in the world, closed around 2002, with price competition from Chinese production among the contributing factors, alongside environmental compliance costs. It later reopened under MP Materials, but by then, the global refining infrastructure had consolidated around Chinese capacity. This consolidation was complete well before semiconductor sanctions became a major policy instrument. The rare earth dominance predated the chip war framing by decades. Nobody drew the magnet layer onto the chip tool supply chain map because the dominance was background infrastructure, not a weapon anyone was tracking in that context. It's like discovering the foundation of a building was poured by someone else, decades before the architect drew the plans. The building went up. The foundation was already there. The sanctions just made everyone look down and notice the floor, which means the loop wasn't built as a response to chip controls. It was already closed. The export licensing regime didn't create the leverage. It formalized it. Now apply genuine skepticism to the strongest claims here, because the story is more nuanced than either its most alarming or its most dismissive reading. 3 honest limits. First, the specific magnet sourcing of any named chip tool vendor, ASML, Applied Materials, Lam Research, is not publicly confirmed. We know the tool category depends on these magnets as a matter of engineering design. We do not have a verified sourcing map saying this company buys from that specific supplier. That gap matters. The category-level claim is solid. The vendor-specific claim is not made here. Second, China's export licensing on rare earth products has not been deployed specifically as a cutoff against chip tool magnet supply. The leverage exists as a policy architecture. It has been used with discretion. The 2023 licensing regime means the permission can now be withheld. It does not mean it has been withheld in this application. Leverage doesn't have to be activated to exist, but the distinction between could restrict and has restricted is real and must not be collapsed. Third, substitution is possible in principle and is being actively invested in. The United States CHIPS Act and the European Union's Critical Raw Materials Act include provisions aimed at supply chain diversification, including critical minerals. Funding a refinery and operating one at competitive scale are different things, and the timelines are genuinely uncertain. But the direction of investment is established policy, not just aspiration. This is a years-long structural exposure, not an impossible one. The pattern this fits into is not China retaliates with materials. The pattern is that the semiconductor supply chain has always had a consequential layer one level deeper than wherever the policy debate is happening. For a decade, the debate was about finished chips. Then it moved to tools. then to tool components and software. The magnet layer, the actuator layer, the physical hardware that moves the wafer, is not glamorous, doesn't have a press cycle, and didn't show up on a sanctions list. It's the layer the debate hasn't fully reached yet. Here is my honest read. Two extreme interpretations exist, and both are wrong. The first says, China has the semiconductor tool industry by the throat on magnets and can shut down production tomorrow. That's not supported. Timelines, existing stockpiles, and the feasibility of substitution in principle make an overnight cutoff implausible. The second says this is just a commodity supply chain issue, like needing a different steel supplier, and the market will solve it efficiently. That's also not supported. The refining concentration, the requalification burden, and the depth of the vertical integration is unnfix. This is a structural exposure measured in years, not a swap measured in quarters. My read is this. The neodymium loop is the clearest example of a supply chain dependency that survived the entire era of chip war scrutiny because it was one layer too deep for the policy debate to reach. That's not alarming in the panic sense, it's clarifying. The work is now visible. And visibility is the first thing. The ceiling the West built over China's chip ambitions, layer by layer, from finished chips down to tools, down to components, down to software, rests on a floor China already holds. The loop doesn't need to be activated to matter. It needs to be on the map. So here is the question I want your honest answer to. In the comments. Given that meaningful rare earth magnet supply chain diversification is going to take years, possibly closer to a decade for the refining layer specifically, does the West need to treat this as a strategic emergency and fund it accordingly, the way the CHIPS Act treated domestic chip fabrication? Or is the current pace of investment through the Critical Raw Materials Act and existing mining programs actually sufficient, given that China hasn't deployed this licensing lever against chip tool supply yet? Two real sides. Which matters more, the structural exposure or the deployment gap? Tell me where you land. Subscribe if you want to follow this specific loop as it develops. When the first Western rare earth refinery comes online at meaningful scale, whether China tightens the licensing regime further, and which tool vendor is first to say publicly where their magnets actually come from. That's exactly what this channel tracks. The most export-controlled machine on Earth, running on a magnet, tracing straight back